So I was asked to give the Geology and Chemistry warm-up talk, and I would like to just apologize to all the geologists in the room to begin with. I'm a chemist, but we'll get through it, and you can tell me what I got wrong at the coffee break. And so I'm fairly simple, and so when I think geology and chemistry, I think rocks and goo. And so we'll sort of see if that's the right depiction or not. And of course, it's not. So when I actually think about geology and chemistry, I think of them as setting the boundary conditions for life. So they're providing the environments and the possibilities of how things could be habitable and what is possible in sort of the parameter space of life and habitability. And I think there are sort of multiple boundary conditions we can think about in terms of how to go with this. And I think there's historical, there's what was present on an early Earth, there's environmental, what is present now on a different planet, or what is present now in the Earth. And then there's also sort of more fundamental physical boundary conditions in terms of thermodynamics and kinetics, what chemistry can occur and how can it occur. And so from that, I think, I mean, it's sort of your classic bottom-up approach in terms of thinking about habitability and life, but I think it's a really powerful tool for getting us towards understanding the actual sort of physical constraints on life as well. And so just to orient everyone to this timeline, I really like this depiction of sort of the Earth timeline. I'm borrowing these slides adapted from Stephen Freeland. It's amazing if you haven't met him. But there's sort of four major geologic eras. There's the Phanerozoic, the Proterozoic, the Archean, and the Hadean. And we're just going to walk our way backwards from there. So I think of the Phanerozoic as sort of the normal geology part of the timeline of Earth. And so up here, really early, we have the extinction of the dinosaurs and the Cambrian explosion. And we're going to be hearing from Amanda about sort of Neoproterozoic geology today. And then around here, we had our earliest multicellular fossils. And then working our way backwards, we have the Great Oxidation Event at about 2.5 billion years ago. And working from there, Chloe is going to be telling us about possible chemistry that occurred from following the Great Oxidation Event. And then working our way even farther backwards, our sort of oldest microfossils and our oldest direct evidence for life are at about 3.5 billion years ago. And our indirect evidence for life is, somewhere between 3.8 and 4 billion years ago, depending on who you believe and which controversies you like to pick. And this is also around the period of the late heavy bombardment, if you like the idea of a late heavy bombardment. And really the period we're going to be talking about most for the talks in the afternoon or in the post-coffee break session are going to be our prebiotic chemistry talks, and they're really quite far down on this timeline towards the formation of the Earth. And one of the interesting things when we're thinking about prebiotic chemistry in particular and the conditions and the boundary conditions for that is that to a large part, we no longer have a rock record back that far because of plate tectonics and because of the recycling of material. And so other than a few sort of detrital zircons here and there, there really are sort of limits on the constraints we have from geology. And so that's really where the realm of the chemist comes in, and they get to sort of play around with whatever conditions they want because we're not super constrained by actual geology. All right, maybe not, but and of course we can also look at this with Mars as well. And so there are also four main timeline sort of eras. Is that right? I don't know. Anyways, four main distinctions here, where we have the pre-Noachian, the Noachian, the Hesperian, and the Amazonian. My understanding is the sort of border between these two is somewhat controversial as well, and where that time should go, I'm not entirely sure. But this is sort of the area where we think that Mars would have had some water and maybe been more habitable, and then this is the dry, cold Mars of today. And so we'll be hearing from Jonathan about some sort of potential stability of biosignatures in the border between the Noachian and the Hesperian timeline. And so when we're thinking about constraining the conditions, we're thinking about what might have been present in oceans, the salinity, the ions. We're also thinking about what was in the atmosphere, what gases were available. Also, were there aerosols or hazes or things like that? And what chemistry can that provide? And also land, like how much land was around and what were the minerals and rocks there as well. And actually, we have most of our geology talks today are actually more focused on sort of atmospheric tracers and looking at atmospheric tracers in the, And of course, we have interactions between all of these as well. And so we're going to be hearing from a few different sort of techniques as to how we can think about it. So there are geologic proxies using elements to sort of tell us about oxygen. And in this case, we're going to be looking at fluorescence with Amanda. We're going to be looking at some analog sites and isotope fractionation again. And so because we've heard a lot about isotope fractionation, I'm not going to go into that. And then also sort of more truly chemical ways of modeling reactivity. What are the sources and sinks of N2O? And as I said, on the early Earth, partly because we don't have a great rock record, there's sort of a lack of constraints as well for sort of when we're thinking about more traditional prebiotic chemistry. And sort of as Saeed showed yesterday, when we're thinking about simple to complex, that's kind of the main trajectory we're thinking of with chemical evolution. And there are a couple ways of thinking about complexity. And people use different terms, but when I think about it, I think of molecular complexity as how we go from sort of simple molecules to more complex molecules, and in particular, how we do that without biology. And so we're going to be hearing about that from both David and Moran. And just because this comes up at every AbGradCon, chemists really like to use skeletal structures, and not everybody knows what that is. So here are a few of my favorite molecules. But basically, each of these are a carbon. So each of the sort of triangular shape here is a carbon, and then there are hydrogens that are sort of redacted hanging off the edge here. And so C3H4O3 is the same as this molecule, and then when it loses a hydrogen, it's deprotonated, and that just comes up. And you can hydrate, or you can do hydrolysis, depending on whether you have a hydrogen or a water or not on there. Okay, so we've got molecular complexity. We've got chemical complexity. What is sort of the heterogeneity of the mixture that was available? What are we thinking about? So there's the foremost reaction, of course, that makes a whole lot of stuff, including a little bit of ribose. And Niraja will be telling us about the role of heterogeneity. And then we also have what I would characterize as supramolecular complexity, and we'll be hearing from all of our organic-y chemists this afternoon about sort of what are the larger 3D organization, and in particular, how do we get towards functionality, and how do we get towards, maybe getting to biology and biochemistry. And of course, we also have to think about, if you're going from simple to complex, what are the back reactions, and how are we going to be breaking down, and how are we not? And in particular, Jonathan's going to be talking about biosignature stability, and what are these possible back reactions, and how we might be missing things. And yeah, just in terms of if we want simple to complex, we have to have sort of overall something pushing us towards more complex structures, and that generally requires an input of energy, and in general, a sustained sort of out of equilibrium system. So I can't give a talk and not mention the sun, because I'm a photochemist, and that's my favorite input of energy. But we also have wet-dry cycles that I suspect we will be hearing about as well as a nice way of sustaining out of equilibrium systems. And then just to remember that we have to think about all of this chemistry in the context of the environment, in the context of all of the other stuff that's going on, and not just in optimization terms, but also in terms of, just what is around. And we can't forget that mixtures are really important as well. And so I would say that our geology talks are roughly atmospheres and rocks. And that our chemistry talks are largely how do we avoid goo. And so with that, we'll move on to the next speaker.